Okay, so let's start with today's lecture. And I want to get a little bit more into random graphs this time around. In the first lecture, I discussed some very basic properties about graphs in general, directed graphs, undirected graphs, cycles, clicks, subgraphs, and many of the topics that are relevant to people studying graphs in general. And again, this class is mostly intended to tell you a little bit more about big graphs, big networks, things like the internet, like Facebook, like Twitter, where we're talking about nodes that are in the millions, possibly, with lots of edges and complex structure. So when we are looking at things like that, it's often that we don't want to actually think about the graph specifically as one instance that is not random, that it's right there. But it's easier to think about our problem as the graph that we are seeing is just a representative of some bigger class of potential graphs that exist out there. And when we think about this sort of typical graph, it allows us to sort of ignore the fact that some of these graphs are changing all the time. You know, any graph like that relies on the internet will constantly change. You know, new people are added to Facebook, people drop from Facebook, new people get befriended, other people get defriended. Whatever it is, the things are changing so much at a scale that maybe what we're interested in is not the specific instance of the graph, but sort of the general properties of what could be many different graphs from one moment to another. When the size of the graph is very large, this is something we can accomplish using a random graph model. And that's what I'm going to be talking about today. All right, so a random graph model, you can think of what is it? Well, it's a model. And the word random refers to the fact that we're going to create this model using some random fluctuations of some sort. From one model to another, how this randomness plays out is going to be a little bit different. Why do we do it this way? Well, once we have a random graph model that can generate many different, let's say, realizations of that model, if we can say something about properties that almost any realization from that model will have, then it tells us something that maybe if our real graph, the Facebook graph today, let's say, is from, you know, shares enough properties with these random graph model, maybe the same properties that we show on the random graph model are going to be true for the graph that we're interested in. So you would think like, I'm thinking of right now Facebook graph as just one element from a model that I'm going to pick. Maybe Facebook graph tomorrow is going to be another sample of that same model, but it's a little bit different from the one today. Because we're going to have to choose a model for deciding, you know, where our graph that we're interested in belongs to, you know, we're going to have to be picky about what properties of the graph we want to mimic, let's say. There is no such thing as a perfect model for everything. You know, any model is wrong, but some models are useful. And in that spirit, what we're going to try to do is we're going to try to choose a random graph model that mimics the characteristics that are important to the problem or the questions we're asking. And what I'm going to do today is I'm going to tell you about several models that have different properties. When we look at random graph models, we're usually analyzing these under some kind of limiting sense. So I'm going to start by saying that a random graph model is going to have a set of vertices 1 through n. Usually, n is going to be large. To each model, we're going to have a set of rules that are going to tell us which edges are going to be there and which edges are not. Right? And these rules are going to follow some random idea. How exactly, as I said, will depend from one model to the other, but the idea is randomness plays a role because this is like throwing dice. You know, on one throw, I get a sum of 7, and on another throw, I get a sum of 10. Each time I do it, we're going to get a different realization. So here, the similarity with the dice throwing consists on which edges are present and which ones are not. And the way that we're going to analyze these observations is under a suitable limiting regime. In our case, it's going to be what we call the large graph limit, which means we're going to take a sequence of these realizations, and then we're going to take the limit as the number of vertices grows to infinity. What is that's going to give me is going to give me a sequence of realizations from that specific model. And we're going to try to use this limiting regime to simplify computations in such a way that we can obtain nice properties that the graph is likely to satisfy. In terms of the kind of theorems or kinds of results that we prove, we're going to be saying something about these random graph models satisfies X, Y, Z property in something we usually call with high probability as n goes to infinity. What that means is that any graph that shares enough of the properties that a random graph model has, and that is large enough to allow this limit sort of to kick in, is going to be very likely to have the properties that we prove. So if we prove that a random graph model is connected with high probability, that means that our real graph, assuming it looks enough like the model that we're studying, is going to be connected with high probability as well. So that's the idea of using this kind of approximation. Now, in great generality, we can think of random graph models in two different ways. The first one is the idea of here's a very, very big graph. I'm going to take a picture, click, and I'm going to get a snapshot of that graph. So it's not moving, it's what it is the moment I took the photo, and we're going to call those static models. The vertices are fixed, and we're just looking at which edges happen to be present when we took the picture. On the other hand, we have models that are evolving or growing that tell us how the graph grows as new vertices come in and get added to the graph. The idea of evolving models is that they're trying to explain not only the properties of the graph at a snapshot, but also how exactly that graph come into being. Why is it the way it is? Why does it look the way it looks? Right? So while static models are a snapshot, a photograph, evolving models have a lot of relationship between one observation and the next one, because all we're doing is we're saying, well, now we have a graph with a vertex set of 200. In the next instance, one new vertex, so now I'm going to have 201 is going to join in. And you can imagine that the two graphs are going to be very close to each other. There are models where we also, as time passes, we remove edges or remove vertices, but there's also many models of evolving graphs where we do not allow any edge or any vertex to disappear, in which case, as we grow the model, the old one from the previous instant is a subgraph of the new one, right? So every vertex that was here is also going to be here. Every edge that was here is also going to be here. That's going to be typical of some of very famous models that you may have heard of. Today, we're going to devote most of our attention into the static graph models. And I have a long list of different examples to give you that satisfy different properties depending what you're trying to study. I'm going to start with the most famous random graph model there exists, which is called the Erdos-Renyi graph. And the Erdos-Renyi graph is essentially the simplest thing you can think of how to create a graph based on some level of randomness. And the idea is I'm going to first fix the set of vertices 1 through n. If I have n vertices, then I can have an edge between any two pairs, and there's a total of n choose 2 possible pairs that I can pick from this graph. Let's start with the undirected case just to keep everything simple. And each of those pairs can either have an edge or not. So the way that I'm going to choose whether that edge is present or not is by tossing a coin. And this coin, if it lands heads, it means that I'm going to draw that edge. If it lands tails, it means I'm not going to draw the edge. Now, just to make it interesting, we're going to allow the probability of this coin to be anything between 0 and 1. So it doesn't have to be a fair coin, right? Whatever we want to pick at, the probability of having an edge is any number between 0 and 1. So specifically, if I have two vertices, I and j, then I toss a coin, If it lands heads with priority P, if it lands heads, I draw the edge between I and J. And if it lands tails, I do not draw any edges. In this notation, the adjacency matrix of the Erdős-Rényi graph can be written as a symmetric matrix. So Aij is equal to Ajj. And this notation means the indicator of the whatever is inside. In this case, what's inside is the event that the coin flip ended up being a head. So if it landed head, this is going to give me a 1. If it lands tails, it's going to give me a 0. And this is true for any I different than J because we do not allow to have self loops in this model. So therefore, without self loops, the diagonal is always going to be 0, which is what this term over here says. So this is the Erdős-Rényi, the description of the Erdős-Rényi graph. And I said it's the original random graph model due to Erdős and Rényi. And it has been studied to pretty much any level of depth that you want. So just to give you an idea of the kind of things that are known about this model, I've collected here a few of the properties that are famous. So let's take a look at the connectivity properties of this graph. So if I have a large enough n and I start throwing coins according to priority P the way that I described, I end up with a graph. If the probability of connecting any two edges is such that P multiplied by n is smaller than 1, then chances are that my graph is going to consist of only isolated components. All of them are going to be fairly small. They're going to be of size log of n roughly. So there's not going to be any big component that has a big chunk of the vertices, but there's going to be many different separate components with a few handful of vertices. Just to give you an idea, even if n is 1,000, log of 1,000 is fairly small. So there's only a couple of vertices that are going to be connected. We're going to have a lot of singletons, so isolated vertices out there as well. And my graph is definitely going to be disconnected with probability close to 1. However, if n times p as n grows converges and p goes to 0, converges to a constant. So if p is of the order c over n, in the limit it converges to some constant c. And if VC happens to be bigger than 1, then what we're going to see is that there's going to be one big component that we call a giant. And what it means to be a giant, it is that it has a positive fraction of the number of vertices in the graph. So let's say that a giant component could have a fourth of all the vertices, it could have a third, it could have epsilon times n, the number of vertices. Any of those would qualify that component to be giant. And you might wonder, well, what happens to all the other components? Is there going to be maybe two giants, one that has 1/4 of the vertices and one that has 1/7 of the vertices, or something like that? Well, that's an interesting question to ask, and the answer is no. There's going to be a unique giant, and the second largest component that shows up is only going to be of order log of n. So it's going to be a lot smaller in the same order of the components that we see in fully disconnected case. Now, we also have a regime where NP is equal to 1, which we call the critical regime. And in the critical regime, something interesting happens. We do have a giant component, well, a big component, bigger than everybody else. However, it's not of size, a positive number times n, but it's actually a little bit smaller. It's of order n to the 2/3. So that's sort of the really fine result that tells us that the largest component is big and bigger than everybody else. However, it's not as big as what we have here to call a giant. And then we have the other interesting cases. So when P is smaller than a constant, just a little bit below the 1 threshold, log of n over n. So now we're looking at probability of connecting a little bit higher than what we were looking at here. So now instead of being of order c over n, they're of order log n over n. And if I'm a little bit to the left of the coefficient 1, then we can prove that our graph is going to most likely be disconnected. And the main argument to show this kind of things is we're going to show that with high probability, there's going to be at least one singleton, one isolated vertex. And when that happens, we know immediately that the graph is disconnected. On the other hand, if I move just a little bit to the right of the coefficient of 1, so 1 plus epsilon log of n over n, then we know that with high probability, the graph is going to be connected. It means all the vertices are going to be in one unique component. Now, when the graph is connected, turns out that we can show that we have the small world property, and the typical distances are actually quite small. They're of order log of n. Even when n is in the billions, distances tend to stay rather small, which is one way of explaining the 6 degrees of separation. You could argue that even when the experiment was done in the 60s, we were talking about hundreds of thousands, probably millions of people that could be potentially connected in the from the origin to the destination. However, the average length of a chain of people, of acquaintances that had to be traveled was only 6. So that is actually consistent with seeing something that is log of n, order log of n. Any questions about these Erdős-Renyi properties before we move on? No? Okay. So what are the things besides the connectivity properties are we interested in? So I said, it turns out that one of the other features of real world graphs that we usually want to mimic is the degree distribution. So what is the proportion of vertices that have a degree equal to k, right? And in particular, in real world graphs, this degree distribution very often is scale-free, meaning that it decays as a power law. And I'll talk a little more about what that means and what the implications of that scale freeness are. So before we go into the scale free case, let me show you how to compute the degree distribution in the Erdős-Renyi model. So in the Erdős-Renyi model, everything can be done fairly in a straightforward way because each edge is a Bernoulli trial, my coin flip. So I have a set of indicator functions that with probability p are equal to 1 and with probability 1 minus p are equal to 0. The degree of a vertex, in particular, let's say vertex I, is just going to be the sum of the edges. Each of these chi random variables here represents one edge. So if I sum them all up with the, of course, the I equals jk is equal to 0, as we saw before, then it turns out that this is a sum of independent Bernoulli random variables, right? So if we ignore the diagonal just to keep the notation a little bit simple, then this is what we call a binomial random variable with parameters n and the probability of these guys being equal to 1, which is p. So this is a binomial random variable, which we can compute its probability mass function by just saying that the probability of a binomial being equal to k is from all the possible heads that I can get, choose exactly k, which I can do in n choose k ways. Each of those coin flips that were ahead were heads with probability p, so I have k of those, so that happens with probability p to the k. And the remaining n minus k coin flips must have been heads, so that gives me this term over here. And because all the vertices are the same, they're indistinguishable from a probabilistic point of view, then the degree of vertex 1 is equal in distribution to the degree of vertex 17 equals to the degree of vertex 123. So they're all equal to each other and they all have a binomial distribution. So sometimes binomials can get really big, and on the interesting regime that leads to the existence of a giant component, it turns out that they simplify quite nicely. So when NP converges to C, we can approximate the binomial using another distribution. And for that, let me show you how we do this. So I take the probability of the binomial with parameters np equals to k. And we said that this is from n choose k, p to the k, 1 minus p to the n minus k. And I'm going to write this down as follows. The n choose k is n factorial divided by n minus k factorial, k factorial. So I'm going to put the n minus k part here. N minus 1, and I'm multiplying here n minus k plus 1, like that. And I'm going to put this already as the, sorry, I'm bringing it the other way around. N minus 1, n minus 2, all the way to n minus k minus 1. That's the n factorial divided by n minus k factorial. And then I'm going to put the k factorial down here. So that's all my binomial term. Then I'm going to put the p to the k here. And before I put it like that, I'm going to do the following. I'm going to put an n and a p to the k. And because I added that n to the k, I'm going to divide one here, 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 all the way to n. So all of these, I have k in total. So far, we have accounted for the binomial coefficient for the p to the k. And I'm missing this piece, which I'm going to write as follows. This is going to be 1 over 1 minus p to the k. And the rest is going to be 1 minus p to the n, like that. Now, if you think about taking the limit over this coefficient, this is n over n, that goes to 1. N minus 1 over n, that also goes to 1. N minus 2 over n also converges to 1. And in general, the last one would be n minus k minus 1 divided by n also converges to 1. So this entire ratio of factorials is actually going to converge as n goes to infinity to 1. This term over here, I do nothing, the 1 over k factorial. And the np, by assumption, is converging to c. So that converges to c to the k. Now, to see what happens to this term, oops, let me undo that. To see what happens to this term, notice that this p must be going to 0, because if np goes to c, then p is converging to 0 as n goes to infinity. Therefore, the limit of 1 minus p to the k, we pass the limit through inside, and that has to be equal to 1 minus 0. So this also converges to 1. So that's this term over here. Finally, the last term I'm going to do separately, because that's the one that you may or may not have seen before, which is 1 minus p to the n. Now, to compute this last limit, what I'm going to do is I'm going to write it down as follows. So this limit as n goes to infinity of 1 minus p to the n is the same thing as the limit as n goes to infinity of e to the n times logarithm of 1 minus p. Right? Natural logarithm, of course. The logarithm of 1 minus p is converging to the logarithm of 1. Remember, p goes to 0, and therefore log of 1 is 0, but the n is converging to infinity. So I have one of those situations, n times 0, something that's going to infinity, sometimes something that's going to 0. So what I do is I use the Taylor expansion of the logarithm around 1, and it turns out that this is equal to the limit as n goes to infinity of e to the minus n times p. That's by using the Taylor expansion, and therefore this is e to the minus c. So here's the entire derivation without my big handwriting. What I did on the exponent is this piece, which is use the first order Taylor expansion, or the the approximation for the logarithm at 1, whichever you want to see it like. And this gives me that this limit is equal to minus c. So when I put everything together, I get that the limit of the Poisson, of the binomial, is e to the minus c, c to the k over k factorial. This distribution is called the Poisson distribution. So in the Erdős-Renyi model, the degree distribution is Poisson with parameter c under the scaling limit NP converges to c. This distribution is definitely not scale-free. Why? Because this distribution is actually has tails that go really, really, really fast to 0. Let me now explain a little bit why this matters. A distribution like the Poisson is something we called a light tail distribution. Mathematically, what it means to be a light tail distribution, it means that you have tails that decrease exponentially fast. That's sort of an easy way to think about it. And when you have tails that are so small that they converge so quickly to 0, that means that most of the probability is concentrated around the intermediate values, in particular, they're concentrated around the mean. When something is very concentrated around the mean, that means that there's not much variability, right? I can throw a coin, I can throw a die many, many times, but it's always, it's gonna, on average, look close to its mean. And in general, I think about a normal distribution where I have something like this. Well, most of the observations are gonna be contained in this piece over here, right? So the Poisson has that property. That means that we're not going to get degrees that are very inhomogeneous. They're going to be all sort of the same, with small fluctuations around whatever the average degree is. On the other hand, when we have a heavy tail distribution, mathematically we have this situation where we have that the e to the epsilon times k times the PMF, the probability mass function. This is the expected value. If you want to write it like that, this is the expected value of e to the epsilon d. This is going to be infinite for any positive epsilon. So around the origin, it's infinity no matter what. And when that happens, we have a very different kind of behavior. This is what we call heavy-tailedness. And it's typical in most real world networks, as you can read about, where the distribution of the degrees decays as a power, usually with some exponent between 2 and 3. Mathematically, what it means to be heavy-tailed is the following. This is a conditional probability that says, what is the probability that my random variable d takes a value larger than k plus m, given that it was already larger than m? If I take the limit as m goes to infinity, I'm basically saying it was big, right? The bigger the m, I'm telling you that my random variable was very big. The fact that this is true for any k over here means that given that my random variable was big, not only was it big, but it was bigger than whatever you already told me, plus any arbitrary quantity. So in other words, given that d is large, most likely, and the most likely is this equal to 1 limit kind of thing, it was not only big, it was huge. So knowing that it's big, it makes it biased to be even larger. And that is the kind of thing that describes heavy tail distributions. To show you and to compare it to what it means to have a scale-free graph, one that is not, Jose and I simulated many of the models that we're going to be talking about today. This one over here is an Erdős-Renyi graph. Jose, do you remember what the average degree for this one is?
Not right this second. I'm going to put it in the chat, okay?
So if I had to eyeball it, it's probably somewhere around 2. You can think this vertex has edges here, here, and here. We have a fair number of singletons, right, that are isolated. But everybody sort of has, this one has 2, this one has degree 2, this one has degree 3, this one has 2, this one has 1. This one looks like it has 2, 1, 1. As you can see, all of them are sort of similar. And that's what I want you to see in this picture. What was it?
Yes, the average degree of any vertices, like of all vertices here is 3.
3. So as you can see, everybody is around 3. There are no big vertices with degrees a lot bigger than 3. And there's, you know, the smallest ones that have degree 0 that is also still very close to 3. So what we see is what we call a homogeneous graph. Everybody is sort of looking the same. There's nothing special. And that is something that doesn't usually happen in real world graphs. So as beautiful and elegant as the Erdős-Renyi model is, sometimes it cannot capture the properties that we see in real world graphs. Because of that, we've come up with many other models that are trying to address that issue. Let me start by telling you about one kind of random graph model that can get the scale-free property without sacrificing too much of the simplicity of the Erdős-Renyi model. So what we want to get rid of is that sort of very well-behaved degree distribution. We would like that degree distribution to be heavy-tailed so that it mimics more what we see in the real world. And at the same time, we don't want to make the model too complicated. So we want to keep sort of the same structure of the Erdős-Renyi, where every edge in the graph gets determined in an independent way from other edges. So just coin flips. The way to fix that is by allowing the probability of connecting any two vertices to depend on the vertices that are being connected themselves. So in this kind of family of inhomogeneous random graphs that we're going to look at, each vertex in the graph is going to be given a weight that we're going to call WI. This is a non-negative number that can be chosen in many different ways. This parameter WI is basically, you can think of this as a degree of extrovertedness that my vertex I has. So if I'm a very, very extroverted person who makes a lot of friends, then I could think of my W being extremely large. On the other hand, if I'm very shy and I don't in general make too many friends, my W is going to be small. So what happens when I look at the probability of having an edge between vertex I and J? If both I and J are extroverted, we want that probability of having an edge to be high, right? So we're going to make it to be equal to the product of the two extroverted levels of the vertices being connected. So if both of them are large, this product WI WJ is going to be large. We're going to scale that or divide it by the sum of all the weights to make the model work and the limiting regime work. And we're going to take the minimum with 1, just because I can't guarantee that this product is smaller than the denominator, and this after all has to be a probability. So with these kind of edge probabilities, my adjacency matrix looks very much like before, except now it's going to be a 1 with this probability that depends on I and J, and 0 with the complementary probability 1 minus that. You'll see how this can change everything. Among this class of models, there's many. So I'm going to give you one in particular, the one that I give you here. There's other ways of choosing this PIJs that are similar, but not quite the one here. This one is called the Chung-Lu model. And what the Chung-Lu model does is also known as the model for given expected degrees. So what we're controlling with the W is that the W represents the expected degree of vertex I. So the expected degree of the vertex, because I'm just summing independent edges, is going to be the sum of the expected value of each of those Bernoulli random variables or indicators that tell me whether the edge is there or not. Each of them has success probability Pij. So the expected degree is this Pij's, which is roughly Wi. I put the roughly and not the equality because in case that this isn't that I have to use a minimum. So if I have to use a minimum, then I actually do not have strict equality. If the W's are such that they're always smaller than the worst pair is always smaller than ln, then I can drop the minimum and this becomes exact. But in general, this is just an approximation, and what it tells us that roughly the expected number of neighbors that vertex I is going to have is that parameter of extrovertedness that we gave it, which is Wi. Now you think, well, how can I choose the Wi's in a way that I can mimic what I see in the real world? Well, let's think about those W's also as a random variable. This, what I have on the right-hand side is the limiting empirical distribution of the weights. So if I choose the weights in such a way that they converge to some distribution F, then what we know about the Poisson distribution tells us that the degree distribution in the graph is going to be very similar to that of F. F doesn't have to be integer valued, but when I take the Poisson and I use a random variable that has distribution F as its parameter, it tends to follow the same shape. So if my distribution F was looking like this, the degree distribution would tend to sort of follow it as well. It's not exactly the same, but it looks very similar. So in particular, if I choose F to be scale free, then my graph will be scale free. So that's how I can sort of obtain the scale free property with the same coin flips that we use to obtain the Erdős-Rényi graph. Just as a little note, the Erdős-Rényi graph is a special case of this where all the W's are the same for every vertex. Again, as we said, we simulated all this model so we can see the difference. This is a Chung-Lu graph where the distribution of the weights of the W's is a Pareto. And the average degree is the average degree of the Pareto, which in this case was what? You remember, Jose?
Give me a second.
Sure, no problem. The idea here is that you can even match the expected degrees in the two graphs, and they're still going to look very different. Right? So you can see in this graph, as if we compare it to this graph where everybody sort of looked the same, in this one, we colored the vertices according to their degree. So these darker vertices right here actually have big degrees. And you can see that from all the edges that are coming out from them. If I could sort of zoom in on this, I could show you better. This is not a dynamic graph, so we'll try to do that for next week. But the idea is as you get closer, these very high degree vertices are connected to a lot of vertices. On the other hand, there's still those sort of isolated vertices out there. And the average degree is, the average is roughly the average of all of this with the exception of those very, very high degree nodes over there. Do you have the average?
Yes, the average, like the average of the Pareto was like the mean of the Pareto was like 3.5.
So that's
so
the
very
mean of
close
this one.
to the previous one, but this one definitely has like vertices that have like very high degrees, right?
And somebody's asking, what is this thing over here? I don't know, is it just, I'm not sure what that is. It's a double edge, yes. I think that's what it is, isn't it?
I think it might be just like a plotting error of some sort.
I mean, there shouldn't be double edges. This is a simple graph. This is probably something, yeah, sorry. It's just something that that got into the plotting of this, but it's nothing. It shouldn't be a double edge. Any questions? Hopefully you can see that this does look very different from the Erdős-Renyi graph, even though as Jose was telling us, the average degree is actually very close. They're very similar. It's just the distribution is different. The tails are very different. And that's what gives us this very different look of how the graph appears. What other properties that we mentioned last time that are important for modeling? Well, one of the things, so now we have the scale-free property, we have the small world phenomenon in any of these two models. The small world property is going to be present for the Erdős-Renyi one. It's going to be present for these inhomogeneous one if we choose the parameters in the right way as well. Distances when they're inside the connected component and the giant component, they are going to be very small, even if the graph is disconnected. But what we haven't talked about is communities. And that's another very important type of feature that we might want to explore with a graph. So when we talk about communities in the context of random graphs, we're thinking about sets of vertices or subsets of vertices that are very connected with each other, but that they're sort of sparsely connected with members of other communities. So when you plot them in the right way, like if you try to plot the vertices in the same and that are close to each other in one color and in different colors, the other clusters, then you'll see that the graph separates into communities, into groups of vertices that have a lot of connections among them, but not so many outside. We also have an Erdős-Renyi type of model that accomplishes this. And for this one, I'm going to assume that I want to generate a graph with K communities. K here is a fixed number. Again, I'm going to start with a vertex set having n vertices. And I'm going to use the value Ci to denote the community belonging of vertex I. So here Ci, each vertex tells me if Ci is equal to 3, that means it belongs to community 3. If Ci is equal to K, it belongs to community K, etc. Same as before, we're going to allow the probability of having an edge between vertex I and vertex J to depend on the attributes of my vertex, which in this case are the community belongings. However, unlike the previous example where the function in which those two parameters were being used was the product, here I'm going to allow it to be more general, and I'm going to call this kappa a kernel function that gives me different possibilities depending on the value of the Ci and the Cj that is not necessarily proportional to the product of the two. The case of the product is a special case that does not give communities in general. This one allows me a little more flexibility to incorporate sort of big asymmetries between what it means, how likely it is for me to connect two vertices in the same community versus how likely it is for me to connect two vertices in different communities. In general, since I have n vertices, I'm going to separate those n vertices into the K communities. And specifically, the size of community K is going to be the number of elements that have label K, right, for their community belonging. So this is the number, and this is going to converge to something in the large graph limit to a constant. This model is called a stochastic block model. And if you want to use a stochastic block model to create communities, what you do is you pick the function kappa, the kernel function, in such a way that it takes reasonably large values when I is equal to j, but very small values when I is different than j. So when I and j belong to the same community, then I want them to connect with a good probability. But when they belong to different communities, I want them to have a small probability of connecting. So that's what this is telling us here. The expected degree now is going to change from one community to another. So if I give you a vertex I and I tell you that vertex I belongs to community M, then the expected degree is the sum of all those Pij's. which are now given by this kernel kappa of M, which is the community of the vertex I, and all the possible neighbors J and their community belongings divided by N. So these are my PIJs. And this is going to be equal after some simplifications to that pi, which is the proportion of community of the graph that community R represents. So once I do the sum and do a little transformation here, I get that this is the expected degree. And as you can see, we can sort of play with it so that we can obtain communities of different sizes. So we can make one community big, one community a little bit bigger, one very, very small, things like that. And we can also change how connected within each community the members are by manipulating the kernel and the size of the community. So it does give you a fair amount of flexibility to create interesting community structures for your graph. And we can use that to analyze many interesting properties about how vertices in the community communicate. So here's again a picture of a simulated graph using the stochastic block model with 3 communities. Also, do you have any, so are they, do you have any idea of what the expected degrees are in each community? Do you remember? No. No.
Yes, this time I got ahead. On average, each vertex is connected to 5 other vertices of their community, and on average, like each vertex in a community is connected to like 0.1 like vertices of any other community. So on average, each vertex will be connected to 5 others of the same community, but probably less than 1 of like others, essentially.
And they all have the same degree, right? It looks like in here.
Yes, the same average degree.
So all of them here in this particular one have the same degree. As I said, you can play with those and make them different as well if that's something that you want to model. So this is a typical picture of a stochastic block model. As I said, the number of communities is whatever you want it to make as long as it's finite. Any questions? No? Okay, so now we covered any degree distribution. We covered the small
excuse me,
world property.
I have a question.
Sure.
Regarding the last graph. What would have taken us to have more isolated points in the graph? What would we have to change if we wanted like well, communities, but with isolated members between them?
And so an easy way to keep the structure, but just decrease how dense the graph is, the number of edges, would multiply the kernel by 1/2, right? Or just make it smaller, all uniformly smaller.
That would make
so just make the probabilities in general smaller. You can make them smaller asymmetrically among communities. I mean, the kernel here is really whatever you want. So here you have the formula for what is the expected degree. If you just want to create isolated vertices, just make that expected degree smaller. And one way to do that is just take half the kernel, or 1/10 of the kernel, as small as you want, and that will decrease the density of the graph.
Oh, all right. And can this model makes it so that the degree the average degree within each community is very evenly distributed, right?
Yes.
Like you can't model communities having like a very unequal distribution within.
That's an excellent question. Thank you for asking that. Indeed, if you think about this piece on its own, if you're thinking this looks like an Erdős-Rényi graph, that's about right. So within each community, this model will treat all the elements of that community as if they were Erdős-Rényi subgraphs, let's say, equally. So the distribution inside the community is always +1. And in that sense, there's nothing interesting happening within communities. You can change the connectivity level of each community. For example, these green ones could be less connected among themselves than the yellow ones or than the blue ones. That is fine, but it's still, the distribution is still Poisson, which means all the elements, all the green elements, whatever the connectivity level is, they're all going to be sort of the same. Some of them might have edges to the outside, but roughly they all look like an Erdős-Rényi graph if you just zoom in into one of these communities. Does that?
Yes, that was my question.
Yeah.
Thanks.
So in that sense, you have to go into more complex models to be able to get intra-community inhomogeneity. That is possible. It's just this one won't do it. Not this sort of simple case. So now we covered several aspects of the things, the properties that we might be interested in. We did this scale-free, the small world, and we even did communities. The one thing I haven't addressed yet is something we call clustering. Now, clustering refers to graphs where the connectivity among vertices tends to be high. And the ultimate sort of measure of connectivity is the triangle. So if we have 3 people on Facebook, 2, A, B, and C, A is friends with B, B is friends with C, how likely is it that A and C are also friends, right? How many clicks do you have? In social networks, when you have 2 people, chances are they're also, or 3 people, chances are if 2 of them are friends, the other 2 are also friends. That's sort of something that is part of human behavior. The measure of that clustering is called, or one of the measures, there's many, is the one that I'm going to refer to here is called the global clustering coefficient, which is precisely what I said, which is the ratio of the number of triangles divided by the number of triplets that are not forming a triangle. So for each triplets that I pick in the graph, how many of those are complete versus how many of those only have 2 edges. So this clustering coefficient usually tells me something about that cliquish structure that happens among vertices. As I said, it's a very, very important feature in social networks in general, because the way that we behave as humans, often we have friends, somebody else comes into the friend group, and that new person becomes also a friend with the existing group, right? So clustering coefficients that are not 0 are rather typical, and none of the models that I talked about right now has any significant clustering. As a matter of fact, under these large graph limit, all the clustering coefficients for the models as I wrote them is 0 in the limit. So that means the proportion of triangles divided by the proportion, the number of triangles divided by the number of open wedges is actually converging to 0 as n goes to infinity. So in that sense, those models are not great for depicting the fact that people like to make triangles, and with triangles you can make clicks, and bigger clicks and bigger clicks. So that's one of the things that we can do, and for that I'm going to have to give you yet another model that can do that. Before I show you what the model, let me be even more specific about what it means that all those other models have asymptotically negligible clustering. As a matter of fact, those models are something we call locally tree-like, which means if I pick a vertex and I look at its neighbors at distance, let's say 10, and I look at all the neighbors, immediate neighbors at distance 1, and then I look at the friends of those, so those are neighbors at distance 2, and then I look at the friends of those at distance 4, and let's say take a look at the 10th level neighbors of a vertex, what I'm going to see is that it looks like it's a tree. And that means that there are no cycles, no clicks, no anything, right? each person, each vertex is connected to only one other vertex from above, and then that maybe from to below. And because of that, there's no clustering at all that can be significant in the modeling. So in that sense, those models are great. And this property of being locally tree-like is amazing for doing mathematics. It's actually a great property to have when we're proving theorems. However, it's not great for actually trying to model real world behavior. The length of those cycles in the tree are usually of order log of n. What it means, what I mean by the big O notation is that they're roughly a constant times log of n. The value of that constant depends on the specifics of the parameters of the graph. But in general, the cycle length, the typical cycle length, so if I give you a cycle in the graph, its minimum length is going to be roughly c log of n for some c. There's very few smaller than that cycles, which means, definitely not a triangle. A triangle is a cycle, by the way, just to confirm. So the fact that those cycles tend to be large and that we have this sort of locally tree-like thing, it means we don't have any significant clustering in any of the models that I talked about so far. Right, so what do we do? Well, we have to move on to another model, and it's going to be probably the last model that I'm going to talk about today. To construct this model, it's a little bit trickier than the others because I'm going to do it in 2 steps. First, I'm going to construct a bipartite graph. So the vertex set that I'm interested in is the set Vn that has vertices 1 through n. Now that I have this vertex, I'm going to have to decide how to connect the elements of this vertex set. But before I do that, I'm going to create another set, AM, that has m vertices in it. To keep it simple, think about Vn as actors in Hollywood. Think about AM as movies in Hollywood. So we have n actors and m movies. I'm going to create the bipartite graph by saying that there's an edge between an element of here and an element of there. If actor J here participated or acted in movie M here. So there's going to be an edge between this set and that set if that specific actor was an actor in this specific movie. Does that make sense? To make this more interesting, I'm also going to make some inhomogeneous assumptions here. I don't want all the actors to participate in the same number of movies. I want Sean Connery to be in many movies, right? So what we're going to do is we're going to do the same trick that we did with the inhomogeneous graphs, which is to each actor, I'm going to give it a parameter WI, which is the average number of movies that this actor has been in. So actors that tend to make a lot of movies have big W's. Actors who just show up in a few movies have small W's. I'm going to define this probabilities PIs as some parameter gamma, that's just a constant that we can move to just what we want. WI divided by n, and again, the minimum with 1, just in case that this number happens to be bigger than 1. Now, with these probabilities, I'm going to choose which movies they belong to. So actor I is going to toss a bunch of Bernoullis with probability pi I against each of the possible movies. And when it lands heads, that means that that actor participated in the other movie. Right? So for each of these, I create edges towards the set AM using these probabilities pi. So now I have some actors that participate in many movies and some actors that participate in few movies because they're determined by this parameter W. As you can see from what we already saw, the expected number of movies that actor I participates on is going to be gamma WI. Now that we have that, we're going to create the connections among actors. And you're probably familiar with this particular graph, which is two actors are connected if they participated in the same movie, right? So using the V set and the A and the edges among between these two, I am now going to create edges among these alone, among the actors themselves. To do that, for each vertex I in this set and the actor set, I'm going to denote Ni to be the set of movies that actor I participated in. So this is Ni is the subset of the movies where actor I acted. Now we're going to define a new graph among actors that says actor I is connected to actor J if they participated in at least one movie together. Right? So if they were together in at least one movie, so if this is not empty, then we're going to say that the two actors are connected. Now what I have is a graph among the actors based on this other connection that is given by the movies. This model is called a random intersection graph. That's the name. And again, just as before, so I got a question saying, what does it mean that this is not empty? And these are sets, right? These are sets of vertices. It's a set of neighbors. So Ni is the number of movies, is a set of movies that actor I participated in. So here, when I take the intersection, are there any movies that both actors I and J were in together? That's what it means. So if it's empty, that means that they've never worked together in the same movie. Does that answer your question? Good. So now that I have defined in this way, again, we're gonna use F to denote the distribution of the weights that we gave the actors when we were constructing the bipartite graph. We're gonna set the number of movies to be proportional to the number of actors. So I have a constant beta. This is also a parameter that we can play with. A constant beta times the number of actors. Then what we know, or what we can prove, is that in the limit as n goes to infinity, the distribution of the number of neighbors of the degree of vertex I in this new graph, the graph among the actors, is going to be equal to the sum of two independent Poissons. The first one with parameter beta gamma wi. This is coming from the number of movies that they participate on. And the second one is just going to be an independent Poisson with parameter gamma. So the degree distribution is now not just one Poisson, but two. One is a mixed Poisson, and the other one is just a pure Poisson with the parameter gamma that we chose. Moreover, these parameters allow us to do interesting things with the clustering coefficient. So if we pick this distribution of the weights to be a power law or scale-free distribution, so anything that decays as x to the minus something for some constant something, then it's going to turn out that we can obtain non-negligible clustering coefficients in the limit. And moreover, we're going to be able to characterize the clustering coefficient of the graph based on the parameters beta and gamma. Where's my gamma here? So under this regime, we can actually obtain any clustering coefficient in the entire range from 0 to 1. So if you want graphs that have very high clustering coefficient, you pick the beta and the gamma very small, so such that the product is small, and you obtain high levels of clustering. If you want the clustering to be very low, you can choose beta and gamma to be very small, right? And if you do that, then you obtain any clustering that you want in between. And just as I did with the other models, here's a quick picture of an intersection, a random intersection graph, where we used Pareto mixing for the W's, for the distribution of the weights F. And what you can see again, it looks very, very different from all the others. And I can show you, here's the triangles, they're everywhere. What's the clustering coefficient for this one, Jose?
The clustering coefficient is 0.68.
This is 0.68, and this looks very, very different from the other examples that we've seen, as you see. Here, there's a lot of clicks by just looking at it. In particular, there's a lot of triangles. So this is a nice model that can do the scale-free property on one hand. You can see the big degree vertices are probably around here, and there's another few over there. But it also achieves a significant clustering coefficient for the graph. So by playing with those parameters, you can do quite a bit. Any questions? Okay, so let me finish today by just giving you a teaser of next week. Everything we've seen so far is about models that are static. They're all meant to be one quick snapshot of my graph, right? One instance for a given n. They don't actually explain how those graphs came into existence. So when we see power laws, the natural question is like, how did they even come to be? Right? Why do we see power laws in the graph? Well, what mechanism produced them to have these vertices that have such large degree, whereas everybody else is sort of normal, right? It's sort of average. Because the static models don't reflect the growth or how the graphs grow, we're also interested in random graph models that can focus on the dynamic process that leads to the creation of the graph. And those, as I said at the beginning of today's lecture, those are called evolving models. And by far, the most famous evolving random graph model out there is something we call the Albert Barabasi model, also known as the preferential attachment model. This model actually tells us, it's going to give us a way of attaching vertices to the graph that explain why exactly is it that some vertices in the graph will tend to have very, very large degrees, where even while most of all the vertices will just have typical average value degrees. So this model is famous because back when the internet was starting, I think one of the questions that they were trying to address with their famous paper on Science magazine was, is the internet robust? Where the power laws come from, and is it robust? Is it going to fall off if fall apart if you take a few high degree vertices out? So it turns out that this model actually predicts that the internet will fall apart if you take a few big servers down. But even if it failed at explaining the reality of the internet, it did a really good job at explaining the mechanisms in which power laws are formed. And why is it that we see that some of the old vertices and graphs that we've seen grow for a while tend to be a lot bigger, have bigger degrees than newcomers, sort of vertices that have been added more recently. And this has to do with preference in the way we attach to a new graph. The idea is that if a new vertex comes in, think about this as a new person on Facebook, and they see, well, there's all these people in Facebook that I would like to befriend, and let's assume that everybody's going to say yes if you try. Who do you want to befriend if you're a newcomer? You want to make friends with the very popular people already, right? With those people who already have hundreds or thousands or millions of friends. You would love to be able to friend those. So you already have a natural preference to try to go and befriend high degree vertices. And the more newcomers come in and do this, the bigger those famous people become, right? Because everybody comes in and they try to befriend you, and they just keep growing and growing and growing. So those vertices that are already very large just keep attracting more and more and more of the newcomers. And that's what this model tells us. Specifically, the way that this is a simple model, the way that we do it is we assume that each new vertex comes in at time I, let's say. We're going to number vertices in the order in which they arrive. And we're going to call di of k to be the degree of vertex I after k vertices have arrived, so at time k. So at each time step, one vertex comes in. When that vertex comes in, everybody who's already there has a certain degree. So this is the degree of vertex I at the time that the kth vertex comes in. At the beginning, if you want to start it, you can start it with one vertex with only one edge, so with one self loop. When this new vertex, let's say k plus 1 comes in, it's going to choose to connect to vertex I with a probability proportional to the degree of I when that person comes. When the newcomer comes in and sees all the vertices, and it looks like, hey, vertex 1 has 1 million friends, vertex 2 has 500,007, vertex 200 has 251. Well, I'm going to pick who to connect to with a probability that is proportional to the degree. This denominator is just the sum of the degrees, so that everything adds to 1. And I can also decide to stay isolated if I want to. So it's probability 1 over the number of edges out there. I can also just connect to myself with a self loop. This model is the original Albert Barabasi model, and has been proven that it produces power laws, as you might want to see them. This is the sort of vanilla flavor preferential attachment model. So I can only obtain power laws of one order. There's, of course, ways of tweaking it to obtain power laws of any order. But in particular, the original model has a property that the degree distribution, as time goes to infinity and we've added more and more vertices, the average degree distribution decays as a power law with index 3. So we'll talk more about this Albert Barabasi model and some of its properties next week. Next week, I also want to talk about how to simulate using a computer most of the models we have covered in today's lecture. That's it for today. So if you have any questions, we're happy to stay for a few more minutes. And if not, we'll see you next week.